So, good evening, everyone. Thank you for joining in the week 4 of this Unsaturated Soil Mechanics course problem solving session. This session will be focused on measurement of state variables. And, this course is instructed by Professor T.V. Bharat from IIT Guwahati. And my name is Satyam Tiwari. I'm a PMRF for this particular course. And we'll wait for a few minutes so that the other people can join, then we'll start the session. Okay, so let's get started. And we'll start this session by solving one of the problem. The problem states the table 11.1 shows the results obtained from a series of rigid wall constant head hydraulic conductivity tests. And these are conducted on unsaturated specimen of sand. Okay. And the length of the length and the diameter of the cylindrical specimen are provided. A constant head was maintained across the specimen so that the pore water flows from top to bottom. The first two columns show pore water heads at two different locations, and these are inside the specimen, and these are measured with the tensiometer probe inserted near the top and bottom, respectively. These points are separated by a distance of 8 centimeter. The third column shows the volumetric flow rate Q, and this for each test at steady state. Then an identical specimen for eight tests are prepared, and the pore air pressure was maintained at atmospheric. UA is equal to HA is equal to 0. Then we need to calculate the hydraulic conductivity function K for the sand. Okay, so let's start with this problem. So here, these two columns are provided. These three columns are provided. So first we will calculate the head difference delta H. So how we can calculate delta H? Delta H is nothing but H1 minus H2. H1 is going to be 0.51 for the first test, and minus plus S2 is 15.81. After solving, we'll get 15.30. Similarly, for other test also we can calculate 1.02 plus 25.50. This will be equal to 24.48, right? So in the similar manner, we can calculate the delta H for all the tests. Yes. Then we need to calculate the H average. Okay. And to calculate the H average, what we can do is that H average is nothing but HA minus 1 by 2 H1 plus H2. So HA we have the, okay, let me zoom it out. The head due to water that is provided as 0. Okay, so it's 0 minus, that's going to be 1 by 2 H1 plus H2 minus 0.51 minus 15.81. So after calculation, we will get the value of 8.16 centimeters, right? Let me get my calculator. Okay, so now for the calculation of the hydraulic conductivity, we can use the formula Q is equal to K into I into A. And at the place of I, we can use delta H upon delta L into A. So we need to calculate the hydraulic conductivity function K. So that's going to be Q into delta L times upon A into delta H, right? So if for the first experiment we'll calculate, then we'll find that the value of Q is given in centimeter per second as 1.30 into 10 to the power minus 1. The value of length is given as 8 centimeter. All values are kept in centimeter per second, centimeter in second. Then the value of delta H, which we have calculated here, is 15.30. That will be multiplied with the value of A. So the area that's the diameter is provided as 6 centimeters, so it will be pi by 4, 6 square. So let's calculate how much we are getting. 1.30 into 10 to the power minus 1 multiply 8 divides by 15.30 into pi into 36 will be multiplied by 4. So we are getting 2.4 0 multiplied 10 to the power minus 3. The unit will be centimeter per second because it is hydraulic conductivity. Right. So this is we are getting for the first test. Similarly, you can do it for the second test. So if we do for the second test, we will get the value of Q is given as 1 1.42 into 10 to the power minus 1. Delta L is given as 8 centimeter, which will be divided by the delta H value. Delta H is given as 24.48 multiplies by the area, that is pi by 4 into 6 square. So let's calculate this one also. Okay, so here we are getting a value of 1.64 into 10 to the power minus 3 centimeter per second. So for the second one also we got, let's calculate one more. So for the third one, what we'll write? We'll write the value of Q. So it's going to be 2.30 into 10 to the power minus 1. The length is already given as 8, and the head difference is nothing but 41.82. That will be multiplied by pi by 4 into 6 square. So let's solve this one and let me know what you people are getting. So I hope you people are getting 1.55 into 10 to the power minus 3 centimeter per second. Similarly, if you calculate for test 4, test 5, test 6, test 7, and test 8, then we will get all the values of hydraulic conductivity, right? So we needed to calculate the hydraulic conductivity function for the sand. So the hydraulic conductivity can be found out using this formula. Okay. So kindly have a look at this question again and let me know if there are any problem with this one. Okay, so I hope this question is understood. And here we have been given the heads, and we needed to calculate the hydraulic conductivity, right? So let's move on to the next question for this session. And this is a research question for the transient flow and unsaturated soils. And we'll be solving one question uh, on the infiltration experiment. So let's see what this question is. The question says that an infiltration experiment was conducted in the horizontal sandy soil or column shown in figure 9.5. So this is, okay, let's go back. So this is the horizontal sandy soil column, and the cross-section area of the column is provided as 100 centimeter square. The cumulative infiltration volume after 20 minutes of testing was determined as 200 centimeter cube. So we need to predict the infiltration rate and cumulative infiltration at 1 hour and 6 hours, right? So this soil column is or the soil specimen is kept at an height of h naught, right? And this at time t is equal to t1, the this volumetric water content is at this point, and at t is equal to t2, it's here at this distance, right? So actually the wetting front is going forward in the x direction, right? So for this question, we need to calculate the infiltration rate and cumulative infiltration at the two particular times, 1 hour and 6 hours. So first, what we'll do here is we will calculate a quantity that is called as optivity. Okay, and it is so absorptivity is calculated using the formula Q upon under root of T. So it's the net volume which have been infiltrated, and this is the time. Okay, so the volume which have been infiltrated will be equal to, this is the total volume, let's say. So we can write, if we are denoting it as V, so Q will be V upon area, okay, and under root of time. So the sorptivity value will remain constant for all time intervals. So if we calculate the sorptivity for the 200 centimeter infiltration, centimeter cube infiltration, so we can write 200 divided by the area. Area is given as 100 centimeter square. So the time, at what time this is happening? So this is happening after 20 minutes. So let's convert it to second, 20 into 60, right? So this will result into a value of 2 upon under root of 180. If we calculate it, we'll get, it's going to be 120, sorry. So if we calculate, we are going to 2 divided by under root of 120. So it's going to be point 1200, 0.058 centimeter per square root of second, right? So the sorptivity value we have obtained is 0.058 centimeter per square root second. This is going to be remain constant. Okay. So now we can calculate the value of total infiltration as well as the rate of infiltration. Okay. So let's say for number one, for 1 hour, if we calculate, then from this formula only we can write the total infiltration Q will be equal to S under root T. So S is 0.058 centimeter per under root second square root, and then we'll multiply it with time. 1 hour is 3600 seconds. Okay. So if we calculate it, we'll be getting 0.58. So we'll get 3.48 centimeter of infiltration have occurred. Right? We multiply it by area, then we'll get the infiltration in centimeter cube. Now, to predict the rate will be nothing but Q is equal to dq upon dt. So if we take the derivative of this one, then S is a constant, and derivative of delta t is going to 1 upon 2 times delta under 2 times under root of t. So it will be equal to 0.058 divided by 2 times under root of 3600. So let's calculate this one also. So it will be nothing but 0.00048 centimeter per second. Okay. If we convert it into centimeter per hour, then we will obtain 1.74 centimeter per hour. Next, to calculate it for 6 hours, we'll follow the same procedure. Q will be nothing but Q under root S times under root of T. 0.058 will remain the same. Root of T will be 6 into 3600. That will be equal to 0.058 multiplied 6 into 3600. So it will be 8.52 centimeter. At 1 hour, the infiltration was 3.48 centimeter. At 6 hours, the infiltration is 8.52 centimeter. Now the rate of the infiltration is dq upon dt. That's going to be s upon 2 under root t, and this will be 0.058 upon 2 times under root of 6 into 3600. So 0.058 divides 2 times under root of 6 into 3600. Let's calculate this one, and we'll obtain a value of 0.0001919 centimeter per second. Converting into centimeter per hour, 0.71 centimeter per hour. Right. So at 1 hour, the total infiltration is 3.48 centimeter, and at 6 hours, it's 8.52 centimeter, more than twice. So have a look at this question and let me know wherever the problem is. Everything is fine in this question, I think, and we can move further. So, in the theoretical class, we have studied about the prediction models for soil water characteristic curves, WCC. One of the model is of Van Winchell model, and this was published in 1980. And according to this model, the bigger theta, or that is the normalized water content value, is equal to 1 upon 1 plus alpha times or a times the metric structure value to the power n to the whole power m, and the m can take m is equal to 1 minus 1 upon n or 1 minus 1 upon 2m. Okay, we have already solved this in RETC software, and here we can see that a, n, and m are clean parameter which are unknown and which will require fitting. So these are called the fitting parameter. They are obtained based on the best fit in the experimental model. Okay, and this A parameter, this can also be designated as alpha. So alpha is having the inverse units of pressure. Right? So the Van Winchen model, it provides more flexibility than the Brooks and Corey model, and it can be used for a wide range of sections, and it's better to capture the sigmoidal shape on the typical curves, right? So this is one of the question where it is written the soil water characteristic curve for a silty loam can be represented. Let's just set recording. Okay, so the soil water characteristic curve for a silty loam can be represented by Van Gunsen model with the following parameters. So the parameter value is given as alpha 0.0028 per kPa. Then the value of n is given as 1.3, m is given as 0.231, theta r is given as 0.030, and theta s is given as 0.322. And we need to calculate and plot the volumetric water content as a function of metric suction head. And we need to calculate and plot the specific moisture capacity as a function of water content. So two plots we need to make. So let's see how we can do it. We will be solving this question using this Van Winchen model. Here we already know the values of theta s, theta r, and a, n, and m, right? A or alpha. So A and alpha are mostly the same because alpha is having the unit of 1 upon kPa. So let's open up the Excel real quick, and we'll make a new sheet where we'll copy. Let's zoom in. We'll make a new sheet where we'll copy this data, then we'll solve it. So here, this is the matrix suction value, and we are trying to solve it over a range of matrix suction value. We are starting from one, as in the final plot we will use a log scale. So we don't want to start from zero matrix suction, right? So we can also extend it to some more values. Let's say 380. Now we, based on this, we'll calculate the value of theta, and then we'll also calculate the value of theta upon del theta upon si, that is the slope of this curve. Right? So let's see how we can do it. To get the value of theta, we will make use of this formula. Let me put it here. Right. So in this formula, if we write, this is not the big theta, but the small theta, that is the volumetric water content. So if we write this formula, that will be equal to theta is equal to theta r plus theta s minus theta r, right? And then it will be multiplied with the 1 upon 1 plus alpha y to the power m to the whole power m, right? So if we type in this formula here, so it will give you first the value of theta r, we'll log this one, plus the value of theta s minus theta r, theta s minus value of theta r, then it will be multiplied with this expression 1 upon 1 plus alpha into the matrix substance value, which is here, this to the power n. Then we'll close this one, the numerator part. Then we'll again close this one and we'll raise up it to the power of m. So that's going to be the value of theta. That is the volumetric water content from the invention model. Now, if we need to determine the uh, del theta upon del SI term, that is the rate. Okay, so that's not exactly the rate, that is the slope. So how we can do that is we needed to determine the volumetric water content as function of matrix substance. That is theta as a function of psi. And, we need also needed to calculate the specific moisture capacity. Okay. So d theta upon dsi will actually represent the specific moisture capacity as a function of water content. Okay. So let's calculate d theta upon dsi. So it will be nothing but the change in the theta value for a small increment minus this one upon change in the SI value. And let's say we want to be positive. Let me check what other values we are getting here. Okay, right. So now if I extend this formation, then we'll get this. Again, we'll plot some of the plots to see what are the uh, how is the trend. Let's see. First, we'll plot this theta versus SI. SI will be in x-axis and theta will be in y-axis. So we'll plot this one and let's see how it is coming. So let's add some chart elements. So this is SI and this is going to be the moisture content, volumetric moisture content. So if we make this SI in logarithmic scale, we will obtain a plot like this, right? And if we just copy this plot and we select the data for this plot, we will change the data to the x value will remain the same and the y value will change it to d theta upon dsi. And let's see, this is the change of this d theta upon dsi over suction range, and this is the change of the volumetric water content over the suction range. So as the suction is increasing, the volumetric water content first remain almost constant, then it decreases significantly. And this is the slope. The slope first increases, reach it up on DSI, then it decreases. Okay, so this trend is obtained. So I hope this question is clear to you. Take your time in this question and let me know if there are any problem. So we have studied the prediction model, and when we come to the suction, we have already seen in the theoretical class that there are several techniques to measurement for the measurement of suction and or the control of the suction. So one of the techniques is handing negative column technique, and in this one we have a soil column which is subjected to a particular head of water. And as you can see here, this is the soil column which is subjected to a particular water head. And then the sensors are provided at different locations to determine the volumetric water content. Based on this experimentation, we can plot the graph between the volumetric water content versus this pore water head, right? And we can determine the suction values. The second technique is the tensiometer techniques. In the tensiometer techniques, we actually have a porous disk here, which is the sensing probe that is inserted into the soil. And using this, we calculate with this instrument, make use of the osmotic techniques for calculating the tension or the metric suction values in the soil. So let's see it. This tensiometer mainly depends on the higher entry disk which is used. Okay, the range of this tensiometer decreases over the time as this sensing probe starts to get clogged and after some time. So right. So if we need to calculate the pore water pressure for a particular HAE capacity, if you want to calculate the metric section and the pore diameter is provided, then how we can calculate is that UA minus UW will be equal to 2 times TS upon R, as we know, taking alpha is 0 because 0 is 1 and neglecting the cost term. So we'll write 2 times the surface tension of water is 72.75 converted equivalent per meter and 10 to the power minus 6, and the diameter is provided as 6 into 10 to the power minus 3. So the radius will be 3 into 10 to the power minus 3 and we'll convert it into meter. So it will come 48.5 kPa. So that's the metric suction value uh, which we can calculate. And just like this, we can calculate the metric suction values that we can measure from these HA capacities in the pore diameter. Then one of the type of technique is the X6 translation technique. Okay. In this technique, the soil sample is kept in this chamber where the pore airways pressure and the water pressure can be maintained, or we can say the matrix suction can be maintained. And the soil is kept on a higher entry disk, and this matrix suction is controlled in this chamber. So this is a suction control technique, and and the probe is inserted and here so that we can take how much water is coming out or coming in. Based on that, we can calculate the value of UL minus UW, the matrix suction. Then there are other type of techniques such as osmotic technique we have studied. In this technique, we make use of the uh, osmotic pressure in which semi-permeable membrane is provided here, and some kind of solute is here, and this semi-permeable membrane allows the water particles to go from one side to another, but not the solute particle. Based on that, we can calculate the value of the osmotic suction in this technique. Then there are other kind of techniques also, dew point potentiometer techniques, where this optical sensing bridge is used to determine the dew point of the soil sample. And so in this technique, let's say we are measuring the suction values are different relative humidity, let's say 0.9999, 0.999, 0.99, 0.91, 0.9, etc. And will you make use of the Kelvin's equation, that is phi t is equal to minus RT upon mu W, that is the specific volume of water, upon molecular weight, ln, vapor pressure, and UV saturation. Okay, so this is nothing but the relative humidity RH. Okay, and we need to calculate the matrix suction values. Total, this WP40 technique gives the total matrix suction. So how we can calculate it? The value of R, as we know, is 8.314 joule per Kelvin mole, and that will be multiplied by the Kelvin. The temperature is 293.16 chamber temperature, and it will be divided by mu W, that is 1 by 1000 meter cube per kilogram, and we will be the MV is 18.016 kilogram per kilomole, and then we'll calculate ln 0.999 for the first set of experiment. If you calculate this one, we will get a value of 13.54 kPa. Similarly, for 0.999 also we can calculate, and so on. So we can calculate for different relative humidity values. We can calculate the total matrix suction. As the humidity will increase, the matrix total suction value will decrease in this direction. Then there are vapor equilibrium techniques, which which is based on the concept the soil slowly comes in equilibrium with the vapor, and then the filter paper techniques are there, which can measure the matrix suction. The contact filter paper technique, which can measure the matrix suction value, and in which the filter paper and the soil they come into equilibrium. And then there are other type of techniques that are dynamic viscosity of both filter paper and soil will come to an equilibrium. And then there are techniques like non-contact filter paper technique, which can measure not only the matrix suction but the total suction values. Okay, so these are some of the techniques which can be used for the evaluation of the matrix suction and the osmotic suction of the total suction values. Right.
In Cole model, we will do a similar exercise for Venn Gunjan model. Okay, so this example which is given, that the previous example which we solved, problem 12.1, we need to solve this using Venn Gunjan model. Okay, so here you can solve it either with and without the values of m is equal to 1 upon 1 minus n constant, 1 upon 1 by n constant, or not. So we'll just solve it for one case. Okay, there where the m will be equal to 1 minus 1 upon n. Fine. So the values which are given here are the same as given for the previous problem. So we'll again switch to the Excel sheet. Okay, so we'll again switch to the Excel sheet, and we will just make a duplicate of this one. Okay, so here I've written the equation for the VC model. Okay, Venn Gunjan model that gives the capital theta is equal to, it is theta minus theta r upon theta s minus theta r on 1 upon 1 plus a psi to the power n to the whole power m. Okay, so here are the observation from the laboratory, that is observed suction, and then we have observed value of saturation here, and we need to fit the Venn Gunjan model in this data, right? So first we have plotted this data in a soil water characteristic curve, that is matrix suction and degree of saturation, or you can switch the axis also. Then we'll apply the prediction equation given by Venn Gunjan, and then we'll plot this data also in the same plot to see how well it is fitting. Okay, then we'll vary the values of a and m and sr to better fit this model, right? So in the last expression, if you'll see, I have predicted the value of the suction. Okay, and in this expression I'm going to predict the value of the soil, the degree of saturation, right? So this is one thing to note, that this expression are reversible. Okay, either you can obtain the value of suction based on the value of theta, or the volumetric moisture content, or the degree of saturation, and or reverse, you can obtain the value of degree of saturation or the volumetric moisture content based on the values of suction, right? So that's why I've done one problem for prediction of the suction and another for the prediction of S value. So to predict the value of S, or the degree of saturation, we can use this expression, and in the place of the volumetric moisture content we can use the degree of saturation also, as they are linearly correlated. So here we need to find the value of S, or the theta. So that will be equal to, if we send this part denominator this side, so this will be theta is equal to theta r plus, in the bracket, theta s minus theta r multiplied by this term, right? So we'll apply this equation here. So let's write the formula. That's going to be theta r, the value of theta r, or sr, is here. Okay, let's first fill some values here. Let's say a is 0.5, n is 0.3, the value of m is equal to n, the value of m is going to be, okay, let's see, that is 1 minus what is given in the question, that's going to be 1 minus 1 upon n, right? So we can use m is equal to 1 minus 1 upon value of n. And the SR, don't mind the values here because we are anyways going to optimize it. Okay, the values of the SR, let's say 0.3 here also. Okay, now we'll write the expression. Let's increase this one to 1 or 0.8. it's okay. Right. So now we'll type the equation here. That's going to be the predicted values of S is equal to theta r or SR. Let's log this one, and plus theta S minus theta r. The theta S is S corresponding to SS. Let's log SS minus SR. Let's log this one also. Okay, and multiplied by this whole expression that is there, 1 upon 1 plus a psi to the power n to the power m. Okay, then we'll write 1 upon, that's going to be 1 plus, in the denominator 1 plus a psi to the power n. The value of the a is here. Let's log this value. The value of the psi is going to be observed suction value, that's going to be here, and we'll not log because we want to vary this value over this table, right? And then we'll close the bracket. Let's the power. Okay, then we'll close this one, and the whole power is to the power m. Okay, the value of m is here, and log this one also. Fine. So this is the predicted value of saturation which we have obtained, right? So here if you'll see, as I plot this, these values are coming here. So now if I do the same exercise as I've done earlier to obtain the predicted versus the obtained value, so here if we reverse the repeat the same exercise to predicted values minus observed value, the predicted value is here minus the observed value of saturation is here, and that's going to be to the power 2. And if we provide the, if we obtain the sum of these errors, then it's going to be this one. So again what I want to do is I want to minimize this error by varying these values. Okay, so again I'll go to the solver and I'll select minimize this error value, the sum of the errors, by varying the values of these parameters, right? I'll click to solve and it has solved. So here you'll see you have obtained a very good fit of the model, right? Using this Venn-Genshin function, Venn-Genshin prediction model. Okay, so at this point you can see for the BC model we have obtained a very good fit, and also for the Venn-Genshin model we have obtained a very good fit here, right? So so in this way we can, by using the spreadsheet, we can easily solve these functions. Okay, easily use these prediction models to obtain the better fit, right? Okay, so let's start with the, as we have discussed two models. The first one was the Brook and Corey model for solver characteristic curve prediction modeling. Then we discussed about the Venn-Genshin model, that's in 1980 for the solver characteristic curve, and we have solved two problems with the help of a spreadsheet to better fit the model to the experimental data. Now there are other models also, such as Fredlin and Zing model in 1994. Okay, so the basic difference between the Van Gunchen and Brook and Corey model with the Fredlin and Zing model, if you see here, that in this model, the volumetric moisture content is related to the value. This is exponential value, the e to the power 1, and the value of the suction. But this formula is not reversible, so you cannot write phi in terms of theta or the volumetric moisture content, but you can write theta in terms of phi, right? But in other two models, you can, these are reversible, so you can write both in terms of other. Okay, so this is one of the example which you can solve similarly as we have solved the two models which we have seen earlier, right? So in this example, if you'll see, the data is given regarding the suction in relation to the volumetric moisture content, and these data are used for two type, glacial till and silty loam. Okay, then it is asked that for glacial till and silty loam, so water characteristic data is provided, and we need to model and compare the WCC for each soil using the Briggs and Corey and Van Gunchen model and Fredlin and Zing equation. Okay, so we can again use the spreadsheet and model these model the Van Gunchen, Brook and Corey model along with Fredlin and Zing equation, right? So this I leave for you to do on your own. And apart from the three famous models we have discussed, there are other models such as Campbell model of 1974, Gardner model of 1958, and Bruscart model and McCree and Bob model. Okay, these expressions, this is theta. These expressions are also, they relate the volumetric moisture content with the suction value. Okay. Here also the this W is the water content at any soil suction. Okay, and this is not the volumetric water content, this is the gravimetric water content. Okay, and here also these two are in gravimetric water content. So we have previously discussed about the hydraulic conductivity function. Okay, how to calculate the hydraulic conductivity function in laboratory. Okay, now we are going to discuss about the models of hydraulic conductivity function. Some simple empirical models and the statistical models are provided to model the hydraulic conductivity function statistically as well as empirically, similar to the case of soil water characteristic curve. So here the first model is the Richards model. Richards model is like a simple line equation, y is equal to mx plus c. Okay, so here the hydraulic conductivity k is related to the suction value, and there are two parameters a and b, which we need to determine based on the experimentation. So it is an empirical relation. Similarly, the Gardner have provided another equation, another model, which relates hydraulic conductivity with soil suction, that is equal to K, the hydraulic conductivity at saturation, that is constant, and A into psi. So here 2 value to the power n. Here two values are there. Okay, these are A and n, which we need to determine based on the experimentation. Okay, so this is also an empirical relation, and and as we have seen in here, like in the Van Gunchen model, there were three fitting parameters. Similar to that, here, similar to this, for the hydraulic conductivity function, we also have these fitting parameters. Right, so these fitting parameters we determine based on the best fit, as we have seen earlier also. So Brooks and Corey also provided the hydraulic conductivity function model, and it is also a non-continuous model where k is equal to ks for less than the air entry pressure value, and for more than air entry pressure, that's going to be ks phi psi b upon psi to the power n. Okay, and in the Campbell model in 1973, it says that hydraulic conductivity is equal to saturated hydraulic conductivity multiplied the volumetric moisture content divided by the saturated moisture content, volumetric moisture content to the power n. N is the fitting parameter here, and these are the empirical correlations, but there are some statistical correlations also. These correlations are based on the distribution of pore spaces, okay, distribution of these voids in the soil matrix. Okay, this section is drawn, and based on this they have calculated these formula statistically. The first formula is of Jackson's. Okay, so the Jackson formula relates the hydraulic conductivity with the value of this high volumetric moisture content at particular particular point of time I, and this at saturation, and this value which you see here, j and I, these are the iteration constant, and hj is the hydraulic head. Okay, and this will see that how we use these equations to solve. Okay, then there are models of Bunden and Mollem. These are also a statistical model derived based on different principle, like Jackson's formula is derived based on Hagen-Pasley principle. Okay, so so based on this Jackson model, we can do one numerical. Okay. So the numerical states that the soil water characteristic curve of a sandy soil is shown in figure 12.15, and this is figure 12.15. The soil water characteristic curve is shown here. Okay, these points you can see, and between suction head, that is H. Okay, or you can draw it phi here also, and the volumetric moisture content theta. The saturated hydraulic conductivity Ks is given as 1.8 into 10 to the power minus 3 centimeter per second. Then we need to use the Jackson formalism to predict the unsaturated hydraulic conductivity function from SWCC. Okay, so the Jackson formula as given here. Okay, it in this formula what we need to do is we need to take small increments. Okay, and in these increments we need to calculate the suction heads. Okay, based on these suction head we can calculate the hydraulic conductivity, right? So we'll see in a while that how we'll do it. Okay, so so to start with, what we'll do, that will start from the volumetric moisture content, that is going to be for the saturation. Okay, then we'll take small increments. Okay, one increment will be equal to, let's say this one is 0.3, 0.32, 0.34 and 0.36. so first increment or the decrement is from 0.36 to 0.34, like that. Okay, so one step will go, and it will take 15 iterations to reach here. All right, so let's see how we do it. So we see here that the degree of the moisture content at the saturation, we can read it from here, is going to be 0.36, around 0.36. Okay, and this for the first increment we have taken theta from 0.34. Okay, and similarly we will consider it for different intervals. Okay, so let's see the formula. We have written for the first increment, the theta 1 is going to be, or the for I is equal to 1, theta 1 is going to be theta saturated, that is 0.36. so we are starting from here and moving in this side. Okay, so the theta 1 is going to be theta saturation for I is equal to 1, so that's going to be 0.36. and as when we'll apply this formula, then in this formula we put the value of I as 1. Okay, then we'll see this 2 into 1 is equal to, and the j will vary from I to m. Okay, the value of m is equal to the number of increments which we are taking. So we are taking 15 increments. Okay, so so for we are taking this for the 15 times. Okay, and then we'll see that for the I is equal to 1, this is going to be 21 into 2. For I is equal to 1, if we'll solve the numerator, this one part, and the denominator, the summation part, then these two will be the same. Okay, so these two will cancel out. Then the value of the k will be equal to ks theta I upon theta s to the power c, and we know that theta I is equal to theta s for this case, for I is equal to 1, from 0.36 to 0.34. Okay, so this one will be 1. So for first condition, k theta 1 is going to be ks only. Okay, now we'll calculate for I is equal to 2. Okay, so for I is equal to 2, we start from 0.34, we move to 0.32. Okay, and so we'll write here k is equal to, let's erase the above part, right? So for I is equal to 2, we'll write theta 2 is equal to 0.34. So we are starting from 0.34 and moving to 0.32. Okay, so the value of ks is going to be 1.8, this value 1.8 into 10 to the power minus 3 multiplied by the theta I value is going to be 0.34, the starting of the second iteration, and the value of the theta s is going to be 0.36, the value of volumetric moisture content at saturation, right? And moving on to the part of numerator and denominator. So here if you'll observe that if we put the value of j as 1, okay, then it will be 2 into 1 is equal to 1, right? And plus 1, so that's going to be 3 minus the value of I is 2, 4, so that's going to be minus 1. So we'll neglect the value which are in minus. So for j is equal to 1, we are neglecting the term. Okay, then we go for j is equal to 2. So for j is equal to 2, if you see here, if you put j is equal to 2, 2 to the 4 plus 1, that's going to be 5, minus I is anyways 2 for this second iteration, so that's going to be 4, so it will be 1. So we'll write 1 divided by h square. So what is h? H is the mean value of the suction head at this particular increment. So if you'll see in this increment, 0.34 to 0.32, then this is the mean value. And if you observe this value, then it's going to be somewhere, if you observe this value, then it's going to be somewhere around 2.7 or 2.6 something. So we'll write 2.75 and to the power minus 2 or h square, right? H square. Okay, let's move to for j is equal to 3. For j is equal to 3, what will happen? This 2j plus 1 minus 2i, that will be equal to 3 to the 6 plus 1 minus 4. That's going to be 3. Okay, so if you'll see the denominator part, that is 2j minus 1, that is anyways going to be same, summation of 2j minus 1 upon h square. Okay, so because there is no I part here, so for all the iterations, this part will be same. So we can calculate this as, for j is equal to 1, it is 2 minus 1, 1 upon 2.4 square, the 4 square, the first one 2.4, for the second one 2.75, third one 2.96, then 3, then at the end for 15 iteration it's going to be 30 minus 1, 29, divided by the value of the 15th iteration is going to be around, this one is going to be 80, or you can write 82. as per the book. Okay, so this is going to be 82. So in this way the denominator is always equal, and we have calculated is a 9.387. Okay, and if we perform this operation in a spreadsheet, then maybe it's going to be easier. Okay, then we do it for j is equal to 3. Okay, so this term will be obtained for j is equal to 3. We have obtained 3, and this term will be obtained for j is equal to 4. If you'll see, then it will be 8 plus 1 minus 4, then going to be 5. So this, and this way we can go up to the j is equal to 15. So 27 upon 82 to the whole square. Okay, so let's erase this thing, and so what did we observe from here is that we need to perform this operation, or this operation we need to repeat for k for the values of j from 1 to the m value, or number of iterations which we are taking. Okay, so we are taking 15, so for the 15 number of intervals which we are taking, right? So in this way we will calculate k theta 2, that will be this thing, k theta 2. Similarly we will do this for k theta 3. Okay, for the third iteration we will do it, and we need to repeat this operation till k theta 15, right? So after repeating this operation for every value of every increment of theta, then we'll see that we have obtained a plot that we have calculated the value of k, that is a function of theta, for every value of volumetric water content theta, as well as for different values of soil suction h, right? So we can plot two plots, that is hydraulic conductivity k versus volumetric water content theta, and hydraulic conductivity k versus h, hydraulic conductivity k versus metric suction h. Okay, so this plot will be the hydraulic conductivity will increase as the volumetric water content will increase. So we'll see, as the volumetric water content will increase to the saturation level, okay, then the hydraulic conductivity will be maximum. Okay, and similar for the suction, as the water content will increase, the suction will decrease, right? So in that case we'll see at the suction will if we see as the suction decreases, the hydraulic conductivity increases, or the opposite, as the suction increases, the hydraulic conductivity decreases, right? So in this way we can use this formula of Jackson. Okay, fine. So there's a question that choose that which statistical method can be used to determine hydraulic conductivity function. Okay, so for hydraulic conductivity function, what are the statistical models which we can see here? So these are Jackson model, Burden model, Mollem model. Okay, let's go back and see the question. So from here we can say the Burden and Mollem model are the statistical model, and Richards and Campaign model are the empirical model. Okay, so we have solved this question using the experimental the statistical model. Okay, now we can solve the hydraulic conductivity function using the model which are there, it's empirical models. Okay, so see this example, that there is a data is given of soil suction head versus relative hydraulic conductivity, and we need to fit a model into it. And which models we can fit? The Brooks and Corey model, the Gardner model. Okay, one parameter, two parameter model. So we'll only, for now we'll only set the one model. Okay, so one parameter model, and the Richards model. Fine. So these are the three models. Okay. And Gardner, we are using a two parameter model. So these are the three model which will be fitting. Okay. The data is provided in this table, and we'll be using these expressions and obtaining the value of these fitting parameters by using the Excel sheet. Okay. So again, let's move to the Excel sheet. So we are trying to do the HCF model. Okay, so maybe we'll do the HCF model for using one method. Okay, so here you see I noted down the suction head and the observed value of hydraulic conductivity. These are provided from the experimentation. Now to predict it, let's say if you are using the Gardner equation. Okay, so where is the Gardner equation? This Gardner equation you will see here. This one is the Gardner equation that provides the hydraulic conductivity is equal to the saturated hydraulic conductivity upon 1 plus a to the power psi to the power n. Okay, so these two parameters which we need to determine, right? So here I have written the value of a. I have written something like 6, or you can write 7, or value of n, let's say I have written 3. Okay, so as I'm writing the value, I'm also plotting it alongside. So you'll see these points, the blue points which you see, these are the observed values of hydraulic conductivity, and these points which are there, the gray one, these are the predicted values using Gardner. How I've obtained this? Just come here. Okay, the value, and let's see, we'll do it again for the Gardner value. The Gardner empirical equations, the Gardner equations to formulate the pair to do the pair prediction model, we'll write that is equal to the K predicted will be equal to K upon, that is K saturation. Let's say the K saturation is 1. Okay, and divided by, and we need to log this value, and that is divided by 1 plus a psi to the power n, right? This one, a psi to the power n, right? So let's move here and we will write the value of a as provided here. We'll log this, multiply value of psi. The value of psi suction head is given here. Okay, then we'll click here and to the power n, and we need to log. Fine. So these are the value which we have obtained. Okay, and there are some discrepancies, I think. Let's see. Okay, so if we copy this one here, then we'll see this model is not at all coming very perfect. So what we need to do, first we'll obtain the predicted minus observed values, the square predicted minus observed value, then we'll sum the error. Okay, now we need to use the solver, but before that let's check the formulation once again, and that is ks is going to be here divided by 1 plus a psi to the power n divided by 1 plus, and we forgot 1 here, 1 plus a to the power, and now it is coming. Okay, yeah, now this model is coming like this, the Gardner model, the gray one, the gray line which you see here. Now we need to optimize these fitting parameters. Okay, so for that we'll need to use the solver. In the solver we will provide that we need to minimize this error, and for that we will need to vary these two values. Fine. And then if you click on the solver, then it says that the value of a comes out to be 25 and n 1.77, and now this model fits very well to the experimental data. Okay, similarly the similar things we can do for Richards. Okay, and similarly we can do for Brooks and Corey. So In the same way, if we do this for Richard and Brooks and Corey, then we'll obtain two more results here. That will give you the predicted values of these two predicted values of hydraulic conductivity based on the suction head data which is available here. So these results are shown here. These three models are available here, and for that the optimum parameter values are also indicated in
So before we go on to the question answers, questions of the week 4, we'll learn about one of the software which we can use for solving the 1D flow problems or the transient flow problems in unsaturated soils. And this is a freeware that is called Hydrus 1D. The 2D and 3D are paid version. And this can be used to solve transient flow problems and using different models which are available in the software. And this has been made by the same developers as of RETC software, which we studied in one of the lectures, right? So let me first show how you can get this software. So uh, for getting the Hydrus 1D, you can just go to PC Progress website and write Hydrus 1D there. Then this link will open. You can open the link and go into the download option. You can download the latest version of the Hydra software here. Okay. After downloading, just extract it and it's a easy install. So here in this page, you can also get to know about this Hydra software and other software which have been provided by these developers and some programs which you can use. Then the support system is also here where you can also see some of the examples which they have solved, the documentation and the books, the Hydrus 1D and a user manual, technical manual, etc. So after downloading it, you can let's switch. I've already downloaded it, so we can directly switch here. So okay, so what we'll do is that we'll make a new project here, and this new project we can name as week 4. Okay. The description can be the transient flow, and let's click OK. Then this project have been created. Now there are several pre-processing units here, the main process, geometry information, time information, print information, etc. We need to fill all those pre-processing units so that we can run the program and obtain the post-processing unit. So let's go to pre-processing. The heading you can provide as per your convenience. I've written the transient flow demo. Then to what kind of simulation you want to do, you can here we are going to do the simulation of the water flow. Vapor flow we have not studied yet, so we can also do that here. Solute transfer also we can do it here, and the heat transport and the root water uptake, CO2 transport, etc. And we can also solve the inverse problem that we have studied in SWCC curve. Knowing one of the variable, we can obtain the other. So by just clicking water flow, we'll just click next, and then this unit will come where we can define the geometry of the system which in which we are going to solve the water flow problem, right? So there are like length you can choose in mm, centimeter, or meter. So here I'll be selecting centimeter. Okay. Let's say we'll keep it at default. Number of soil materials, one material. Number of layer, it can also manage several number of layers of soil. And this decline from vertical axis is 1 for vertical and 0 for horizontal. And the depth of the soil profile we can mark here. So I've taken 100 centimeter of depth. That is going to be 1 meter depth of soil. And then we can click next. And here we need to provide, we are on the first process, the main process, then the geometry, then we are coming to the time information. So in the time information, we need to define that for how much time we want to simulate these conditions. So either you can choose in seconds, minutes, hours, days, or years. Okay. So let's say if we choose in minutes, then what are the units we are going to use? So you can choose the initial time, you can choose the final time for how much time you want to simulate, and then the initial time step from where you want to start, and the minimum time step, that is the increment, okay, and the maximum time step. So these are the time information used for the simulation, and then you can also use the boundary condition. Those are time variable or boundary condition which changes with the time. Okay, and I'll just leave it at default again, and we will see what are the next settings which are there. So we are here in the time information. If we click next, we come to the print information. In the print information, we have several options here. The T-level information we can print on regular time intervals. Okay, and these time intervals we can select from here. Okay, and then screen output we want, etc. So these values you can leave mostly on the default. And let's say we want to print on several timestamps, let's say 5, then you can click to select which time you want to print in. Okay, so I'll just leave it by default on 5 timestamps. Let's click OK, and this information is already filled. And if we click next, then we come to the iteration criteria. So in the iteration criteria, we require to fill in the information regarding the iteration or the calculation procedure that will take place. So maximum number of iterations we need to provide. Okay. And the water content, etc. These are values which we need to. So we can increase the maximum number of iterations so that it will run for to obtain to converge on a more optimal point. And water content tolerance, pressure head tolerance, etc. You can provide here. Lower limit of tension interval, upper limit of tension interval. These are all values you can play with to obtain the better results. And then if we click next, then it asks for the soil hydraulic model. So this is the model which there are several models which are available here, which we have studied Brook and Corey model, we have studied Van Genchen model, okay, and Kasungi model. We have also seen the formulation. So here you can choose that which hydraulic model you want to use. Uh, okay, so that will be used for the prediction, right? And then dual porosity model and dual permeability models are there, which we have not yet studied. And if you want to simulate the hysteresis behavior, also we can choose in that here, right? So for now, we are going to choose the Van Ginchen model. And we are not going to choose this air entry value for -2 centimeter. Okay. So we'll choose the Van Ginchen model. So let's click next. And then these are the initial property. These are the parameters which are written here, like the value of QR, the QS value, okay, residual value, and this QS value, the alpha value of the Van Ginchen model, N value, K value, and I value. Okay, these values are selected based on the which soil type which we are using. Okay, so if we change the soil type, we can these values will be changed, or we can also type these values manually if we have the information regarding them. So, like if we change the soil type, these values will change. Let's see. So these are changing. So for now, if I choose the loam, then we can choose these values, right? And the neural much strong version is also here, the neural network prediction value. Okay, their temperature dependency can also be considered here. So these are some advanced level of things which we can learn from the manual, and we can do it here. Then if we click next, then here the water flow boundary conditions we need to define. So what are the boundary conditions that are there? The upper boundary condition is that can be constant pressure head, that can also be constant flux, that can be atmospheric boundary conditions with surface layer, atmospheric boundary conditions with surface runoff, and variable pressure head flux, right? And then the lower boundary conditions also we can define. Right. So in the upper boundary condition, we are defining as constant pressure head at the top level. Okay. And the lower boundary conditions are the free drainage. Free drainage is at the bottom, right? And the initial condition is provided in terms of the pressure head. Okay. So taking these settings, if we go next, then it will ask if we want to run profile application. So yes, we want to run profile application, and we will need to save our data before running this application. So we'll click save. So this is the profile which is visible here. This is the profile which is visible here, and here you can, if you go on, there are several options which are presented here. So if you go on this option, initial conditions, then there are no such initial conditions that are provided. Okay, and uh, then you can play with these options here and provide sub-regions, or if the multiple layer is provided, given the observation points, etc. So now if you close this one, this summary profile will be here. So here if you see that at the top layer the head is given as -100, so we can convert it to 0. At the top layer we want 0 head, right? And the other values are given here up to 100 centimeter. Yeah. Okay. So these are the soil profile summary, which we can see here. And now, if we go further and click next, then it will ask you if you want to run the Hydrus 1D application. So I'll say OK. Do you want to save the input data before executing Hydrus 1D? You'll say yes. So now we have this command window here, which is required, which is there to run the Hydrus program, which we have, which the our project. So if you press any key, then it will run automatically. So it ran very fast, as we see. And here are the post-processing results which are available here. So we can, what are the results we can see? We can see the profile information, right? We can also see the water flow, etc. So for now, there are no results here. So let's change some of the things here, like the geometry will be okay. Click next, okay. Time step is okay. Print information is also fine. Iteration criteria, let's say to 10 we want to solve. Next, the invention model is fine. These values are also fine. And then here we can say lower boundary condition, also constant pressure head maybe. And in pressure, click OK. Now we want to go to summary and click next. We want to run the program again, and it's running. If we click next, then we get this profile information, right? So in this profile information, you can read several information. In the horizontal variable is pressure head that you can change to water content also, okay? And the vertical variable is depth. So against the depth, you can read different like the theta. So as we see from 0 to 100 centimeter of depth, the theta is this depend on the time stamps and different time stamps. So if we put the x value as pressure head, then the pressure for the time stamp decreases significantly, then it remains the constant. So I think we need to play with other parameters so as to get more reasonable results. And we can also see for the water content, hydraulic conductivity, how it is varying over the depth, and the water flux, how it is varying, and the root uptake, etc., how it is varying, right? So, uh, and we can see the water flow, etc. So it's too big, so it cannot be shown. The hydraulic conductivity property, the theta versus H plot is here. So the theta is decreasing as this H is increasing, H in centimeter. Okay. So here also you can change the variable, the water content versus hydraulic conductivity, effective water content, log pressure, etc. Okay, and you can export this into a PDF, and then runtime information file is also big to display. Mass balance information is here. Okay, these are the information which we actually get. So I've run it previously. Maybe let's see if the better results are present there. So in which if you'll see the profile information, then at time 0, the head was like this. At time 1, it is increased to here, it decreases to here, and at the time increases, this head is taking this profile, right? So the head values are changing over time. Water content is changing like that. Hydraulic conductivity is also changing. Right? Water flux is changing. Root uptake we have not calculated, and solid flows. Soil hydraulic properties, that the pressure based on the water content. If you see hydraulic capacity, then it will increase, then decrease. Hydraulic conductivity is increasing as the theta value is increasing, and effective water content, then log pressure head, etc. These values we can obtain from here. Apart from that, this program can also be used to solve the contaminant transport problems and the vapor flow problems, etc. So this is a very valuable program which you can use for different type of flow problems in saturated as well as unsaturated soils. So it's better that you people give it a try and have a look at the manual. Then you'll get to know more about this program. Okay, so now we'll move on to the next questions for the week 4. Now we'll be jumping to the assignment question for week 4, and we'll try to see the answers for these questions. So the first question is that when zero point 0.5 mole KCl is added to water, the vapor pressure increases significantly. So if you read the experiment, it is said that some salt is added to the water, then it is asking that if the vapor pressure will increase significantly. So this is what we know, that as the salt is added in the water, the surface area that is available for the solvent to vaporize, which is always lesser. So less surface area is available for the solvent to vaporize. Therefore, the vapor pressure will decrease. And the statement reads that after adding this salt in the water, the vapor pressure will increase significantly. So this statement may not be totally correct. Let's move on to the second question. That is, the filter paper technique is useful only for metric suction measurement. So as we have studied here, that this contact filter paper technique is used for mostly the metric suction measurement, but this non-contact technique can be filter paper technique can be used for metric suction as well as osmotic suction. So the total suction measurement. So the contact filter paper is used for metric suction technique, suction measurement, and the non-contact filter paper is used for the total suction measurement. So this statement is not fully correct, and that the filter paper technique is useful only for the metric suction measurement. The third question is that two duplicate bentonite soil samples are compacted in air-dried condition. Both samples are connected to different water reservoir. One is having an elevation height of 120 centimeter, and the other is having an elevation height of 240 centimeter. If the flow is allowed to take place under such condition, then the rate of movement of wetting front along the soil samples will be same in both the cases. So this is the head, which is the 120 centimeter for the one sample and 240 centimeter for the other sample. So it is asked that if the rate of movement of the wetting front will be same for both or the different. So if we see by the formula, the distance which is covered by the wetting front after a certain amount of time t will be equal to 2 times under root of k naught h naught minus hi upon theta naught minus ti. This term which is written here, that is actually constant, and that will be equal to, that is actually written as a constant d. So this x will be equal to under root of d times p. So the rate, if we talk about x upon t, it will be equal to under root of d. Okay, so it will not depend on the head. That's why this statement can be considered as correct. The fourth question reads that for relative humidity higher than 90%, the suction value for fine grained soil can be accurately estimated by dew point potentiometer technique. So, in the theoretical labs, we have studied that at very high values of humidity and suction values, humidity, the suction values are very sensitive. Therefore, we cannot establish the suction values when the humidity is very high. Okay. So, at very high values of RH values, it is difficult to measure the suction values accurately. Right? So, the dew point potentiometer techniques cannot be used very accurately when the humidity is very high, mostly more than 90 to 95%. Then we have the fifth question, that as the water content of the soil mass decreases, the flow rate also decreases. So it is true, as we can see that when the soil is fully submerged in water, the flow can easily take place. But as the soil start to deplete water, in that case, what will happen is that matrix suction will come into picture, and also there will be resistance due to air. Therefore, the flow of the water will be restricted. That's why the flow rate will decrease. So this statement is true. To have a look at the sixth question, that says that using the X6 translation technique, the hysteresis behavior of the soil water characteristic curve cannot be obtained. So while this statement is partially correct that X6 translation techniques are valuable methods, and they are widely used for determining soil water characteristic curve, and they may not be able to fully capture the hysteresis behavior, but still they can be used to capture somewhat the behavior of hysteresis in the soil water characteristic curve. Therefore, this statement is not fully correct. The seventh question reads that the maximum value of suction that can be measured from tensiometer is limited to air entry value, that is AEV of high air entry ceramic disc HAE. Okay, in that case, we can say that the maximum value, actually the range of the suction which we can measure from the tensiometer, it is limited by the air entry pressure of the porous ceramic tip and its capacity for the water to sustain high negative pressure without cavitation occurring. So the cavitation is the phenomena which actually restrict the maximum value of the suction which we can measure. Okay, so this cavitation mainly does not allow the measurement to go beyond 100 kilopascal. Even there, the air entry of the higher entry disk allows it to use for more than 100 kilopascal, but this cavitation will not allow to go beyond this. So this statement is not truly correct that the high air entry disk, ceramic disk will not allow the measurement to go beyond a certain limit. The next question is that if the air pressure is more than the air entry value of high air entry disk in the excess translation technique, then cavitation will occur. This statement is not really correct. And the last few questions are that the total section of the unsaturated soil can be measured using dew point potentiometer technique. So as we have seen that dew point potentiometer technique can be used to measure the metric plus osmotic suction that will be equal to the total suction. Right. So in the last question, it has been asked that appropriate technique for laboratory suction measurement of the sandy soil. So for the sandy soil, the dew point potentiometer does not work very well in the laboratory. That's why the tensiometer, contact filter paper techniques, and the excess translation techniques works better in this case for the sandy soils. So these were all the questions which are given in the assignment 4. And now I'll request if you people have any other questions to ask. So if later on you people have any question, you can send me by email or in the next class also you can discuss. So thank you everyone for joining. I'll close this session here for the week 4. Thank you.